Hello, good afternoon to you all members. You are welcome to our second presentation on atomic structure and bonding. The last time we had a lot of discussions held that were about the nature of an atom, and we also managed to look at personalities in chemistry who did a great job in doing analytical work on materials and who had very good conclusions made out of their observations, and their postulates are the ones that we discussed, and we relied on them to imagine and also actually accept that probably an atom looks like the way it looks or appears the way it appears. This time round, we want to look at the way our earlier scientists in your earlier studies of chemistry in secondary schools, you must have handled the periodic table, and our friends out there, at least they must have looked at the different elements, their names, how the names came up, and then if anything, how do we organize these elements in some particular order. So that is what generated what we call a periodic table. So you must have looked at the history of the periodic table, including the personalities who tried to arrange these elements in a table, from the very first ones up to the ones that are now referred to as the modern periodic table. The way our elements that are known are arranged, they are arranged in such a way that the number of electrons, which we said is equal to the number of protons in an atom, and if it is equal to the number of protons, that means that we are talking about the atomic number. They looked at the atomic number and have arranged these elements according to the atomic number, with the least being the first and going onwards as the counting goes on. When you look at this periodic table, it therefore generates an arrangement in which we have rows and columns. The rows run across our presentation, and then the columns run down. So the columns are referred to as groups, group 1, group 2, and so on and so on. We have up to 8 groups, and when you look at the atoms and the atomic numbers of these particular atoms of the different elements, you will realize that hydrogen, which has 1 as its atomic number, has been given position 1. It is in column 1 and row 1. The rows are called periods. The columns are groups. You will find that all the atoms that we refer to as being in the same period, they have the same number of electron orbitals, the same number of layers or levels of electrons that can be occupied. So you will find, for example, hydrogen is followed by helium, which has only 2 electrons. Both these ones are in the same period. Hydrogen having 1 electron in that first orbital, 1s, which is supposed to have a maximum of 2 electrons, there is only 1. Whereas helium has 2 electrons, they are still in the same 1s orbital. So you can see that both these ones have 1 electron orbital, or 1 we can call level that can be occupied by electrons. So it's only 1. We talked about these orbitals in our last consideration or our last presentation. When you look at the ones that follow, lithium with atomic number 3 is now coming into the first column. For helium, it was in the eighth column. The eighth column has all those elements that have a full outermost orbital, meaning helium has a duplet number. Its orbital is full. Later on, when we get to our period 2, you will find that neon follows helium. It has 10 electrons, but the way the 10 electrons are configured, or the electronic configuration in neon, is such that we have 8 electrons in the outermost orbital, meaning that it is full. It is a full outermost orbital, and therefore even neon appears to be in group 8. So all members of group 8 are those ones that have a full outermost orbital, and therefore they are sometimes referred to as inert. They are inert gases. By the way, for your information, they can even exist as atoms independently. When you look at our row 2 or period 2, we said lithium has 3 electrons, 3 protons. You will find that we have in the first orbital, 1s orbital, there are 2 electrons, followed by 2s orbital with 1 electron in it. That is the kind of electronic configuration that we have for lithium. For beryllium, with 4 electrons, we have 2 electrons in 1s, and we have 2 electrons in 2s. But at the second level, we have p orbitals that we discussed earlier. It implies that beryllium has vacant p orbitals, 2px, 2py, and 2pz. When we come to boron, which is in group 3, the ones that have been labeled 3a, all those that are labeled 2a, 3a, 4a, 5a, 6a, 7a, 8a, all those are the ones in the main block. But we have a block which I have not talked about, which is in the center, where groups have been labeled as 3b, 4b, 5b, and so on. Those ones are elements that we sometimes refer to as transition metals. In this particular consideration and our particular lecture discussions, we are going to omit those ones, although amongst them we have metals which are commonly used in our life and we interact with them, but they will be for another consideration later on when you handle transition metals chemistry. That's when it can come up. For purposes of just talking about these ones, in period 2, we have, after boron, we have carbon, we have nitrogen, we have oxygen, we have fluorine, and neon, which we talked about. In period 3, we have sodium, magnesium, then we have aluminium, silicon, phosphorus, sulfur, chlorine, and argon. When you look at all these ones that I've mentioned, the ones which are in the same period have the same number of electron orbitals, whereas those that fall under the same kind of groups have the same number of electrons in the outermost orbital. And therefore, they have relationships, they share properties. The way they react, the way they actually, the way they normally relate to other elements or atoms is the same when they are from the same number, from the same group number. So the reactivity of group 1 elements is the same, although we also have relationships across. That means along the period we have a relationship. These particular atoms relate to one another, and we also have diagonal relations. Going forward, the elements that are arranged in order of increasing number of protons or atomic number from left to right in periods, and the elements in the same period share the same number of outermost shell, but with different number of electrons. Elements in the periodic table are also stacked on top of each other in columns called groups. Elements in the same group have the same number of outermost valence electrons. The valence electrons are involved in all chemical reactions and determine the bonds that atoms make. The rows and groups in the periodic table reveal trends in the electronegativity of atoms. Electronegativity describes the tendency of an atom to gain or lose electrons, as well as its tendency to attract electrons to itself. Electronegativity, therefore, is a very important property. It's a very important property when we talk about atoms. The tendency for an atom to gain or lose will mainly come from the number of electrons that are there in the outermost orbital. We find that the rule is very simple. Those that have very few electrons in the outermost orbital have a tendency to lose or to give away, whereas those that have a big number of electrons in the outermost orbital, they normally tend to gain or to take up or to attract electrons towards themselves. That's what we refer to as electronegativity. Electropositive atoms give up electrons to form cations, whereas electronegative atoms gain electrons to form anions. The electronegativity increases from left to right within the periods of the periodic table, as well as the number of electrons and the effective nuclear charge. Here there are three properties being mentioned, that as we move across the period, electronegativity increases. It increases from left to right, meaning as we move from group 1 to group 7. And then we also find that also the number of protons are increasing. And it has an implication. Protons are found in the nucleus. Therefore, it implies that the effective nuclear charge keeps on increasing as we go towards the right. This has been put in an extract of the periodic table in this way. Electronegativity values have been ably represented here in the periodic table. The earlier arrangement had the number of atoms, the number of protons in the atoms, which we refer to as atomic number. But in this particular extract, we have the electronegativity values here being represented in the form of the periodic table, where we see that hydrogen has 2.1 as electronegativity value. When we get to helium, nothing. Reasons: it has a full outermost orbital, therefore it has no tendency of attracting or giving out or taking up electrons. Therefore, when we look at the second period, we have lithium has 1.0, beryllium has 1.2, boron has 2.0. As we continue across the period, the atom or the element with the highest electronegativity value is fluorine with 4.0. In the third period, sodium has 0.9, magnesium 1.2. The observation we can make here is that group 1 and group 2 up to group 3 elements, they tend to have a very low electronegativity value. They are more electropositive than the elements in group 5, 6, and 7. When you look at group 4, mainly the elements that form group 4 are not metallic. Group 1, 2, and 3 are metals. Those are metals. Whereas group 4 does not have metals, but it has non-metals, in which we have carbon, silicon, and others. As we move across, we find that group 5, group 6, and group 7 elements tend to form, they tend to have atoms coming together to form molecules, and they exist as gases. For example, nitrogen can exist as a gas, oxygen as a gas, fluorine as a gas. The same thing applies to chlorine as a gas. We can also have sulfur in form of gaseous state, but this one mainly exists as a nanometal, even phosphorus as a nanometal. But what we are going to realize here is that the group 7 elements have the highest electronegativity values. When we come to other discussions here that we can give, in group 1 and group 2 atoms, we find that group 1 and group 2 atoms give away electrons to form cations, whereas group 7 normally acquire electrons to form anions, like we said earlier. Electronegativity within a group of elements decreases as the period number increases. That is, when we are moving from top to bottom. Because of these trends, the most electronegative elements are located at the top right of the periodic table, with fluorine being the most electronegative. The concept of electronegativity is fundamental to understand how atoms interact with each other to form molecules. Atoms form bonds. Before we go into or we delve into the explanations of bonds, you as chemists have to realize this. If we are to compare bonds to what we have in real life, a bond is a relationship. In real life, in your family, you are related to your parents, you are related to your siblings. The way you are related to them forms what we call a relationship. The relationship you have with your brother makes you connected to them. But physically, there are no strings between you and your brother. Now, going to atoms. Atoms connect with each other through chemical bonds to form molecules. Electronegativity strongly influences how atoms interact with each other and how they combine to form molecules. Electronegativity difference between two bonded atoms determines the nature of the chemical bond that forms between them. Large electronegativity difference causes atoms to form ions or ionic bond. If it is small, the bond formed is covalent. An ionic bond is an electrostatic attraction between two adjacent oppositely charged ions. Ionic bonds can form when two ions come in contact with one another, or they can form when two uncharged atoms react with one another to form oppositely charged ions. The more electronegative atom strips an electron or electrons from the less electronegative atom, yielding an ion, an anion, and a cation that are electrostatically attracted to one another. An ionic bond is formed when electronegativity difference between atoms is greater than 1.7. An example that I give here is sodium and chlorine. The difference between them is what gives us the kind of bond that we get. We have 2.1, whereas Two atoms form a covalent bond when their electronegativity difference is smaller than 1.7. Examples: carbon and hydrogen, oxygen and hydrogen, then carbon and oxygen. The difference between electronegativity values for carbon and hydrogen is 0.4, for oxygen and hydrogen is 1.4, for carbon oxygen is 1. Therefore, we have covalent bonds formed there. Some covalent bonds involve an equal sharing of electrons between atoms, known as polar covalent bonds. An example is oxygen, where oxygen has a electronegativity value of 3.5 and hydrogen has 2.1. The electrons shared between oxygen and hydrogen do not reside along the plane or along the internuclear zone or exactly between the two atoms. No. We find that because of the electronegativity tendency of oxygen being higher than that of hydrogen, electrons reside closer to oxygen than hydrogen. This results into the formation of partial positive charges. So there's a partial positive charge formed on hydrogen and a partial negative charge formed on oxygen because of the residence of the shared electrons. The bond therefore becomes polar. So covalent bonds which involve unequal sharing of electrons between atoms results into formation of polar covalent bonds with partial charges. Multiple covalent bonds involve the sharing of more than one pair of valence electrons between atoms. Double and triple bonds involve the sharing of 4 and 6 valence electrons respectively. The formation of bonds releases energy, whereas the cleavage of bonds requires energy. Bonds, therefore, form because favorable interactions between orbitals and the electrons in those orbitals allow the system to become more stable. Release of energy during bond formation results in a bond of lower potential energy. The formation of strong bonds involves the release of more energy. Thank you very much for your attention, and we shall be meeting in our third presentation.